Now I shall share my screen. Hello everyone. Welcome to Multimodal Weekly. This is a virtual webinar series hosted by a startup called 12 Labs, which is where I'm working at. For context, we are a Series A startup building multimodal foundation models for video understanding. So, this is an initiative that we've been doing over the past almost 2 years now. We've been meeting on a weekly basis where we discuss a variety of topic ranging from news research in multimodal AI and foundation models, because this is the core kind of focus at the beginning, right? Like curate a great group of researchers to talk about this kind of topic. Oftentimes we also have other persona, like maybe developers who build interesting application in variety of different verticals, startup founders, entrepreneurs come talk about their projects, sharing that with the community, partners from partners who work with our technology and tools and talk about that. You know, we have team members internally come talk about like how to use our platform and API as well. So in some of the recent session, we, as you can see here, have a variety of different topics ranging from, benchmarking multimodal models to interesting like autoregressive models that perform things like reasoning and sound generation to, multilingual multimodal models, text-to-video retrieval, etc. So these are the kind of things that like our community is super excited about. So for today's session, we'll have two presentations. Both are somewhat loosely related to kind of our focus. So the first presenter is going to be Shirley Wu, currently a PhD student at Stanford. She will present a work called Avatar, a novel and automatic framework that optimizes LLM agents to effectively use their provided tools, improve its performance on a given task and domain. Really excited about this. Obviously, to use an agent has been a very I'd say popular topic within the research community and even industry as well. So excited to hear more about her work on this domain. And then secondly, we have Zechen Bai, currently a PhD student at the Shaw Lab at NUS, National University of Singapore. He will present his work called VideoLISA, a video-based multimodal LLMs designed to tackle the problem of language-instructed reasoning segmentation in videos. This is a great work that combines reasoning capabilities and core knowledge from LLMs, as well as some augmentation by the sound model from Meta. So that's some high-level details about our presenters. Just one quick logistical note: if you have any question, feel free to send them on the Zoom chat, and then after each speaker finish, we'll have a short, maybe 5 minutes Q&A for any interactive, question answering. So with that, I will stop sharing my screen, and Shirley, I will unmute you, and feel free to start sharing the screen and do the presentation.
Sounds good. Thanks for the intro and thanks for the invite. So I'm gonna introduce our work Avatar, which is a general framework that's trying to optimize the LLM agents on specific tasks. So for a little bit of background, we now have like large language models that are trained on general and web scale knowledge, but oftentimes people come with their customized data or tasks. And then there's this problem about how to adapt those LLMs or LLM agents in task-specific to task-specific knowledge. So within the scope of those tasks, the tool usage of function calling has shown to be commonly used by people, and because they are powerful at solving complex tasks. And with those tools, you can ask the agent to come up with a sequence of actions or observations that eventually lead to a solution, which is great. However, sometimes we see that I think this might be the experience from like people who actually use the agents as well, that those agents may not use the tools properly. So I'll give one concrete example. So we have a specific task that's trying to ask the agent to generate a sequence of, say, retrieval actions and retrieve, say, some products in a product knowledge base. So the query could be like, can you suggest any TU essays reference that has a split frame design for better proportion? And this agent is given with like an action space, say a bunch of APIs implemented by the users. However, to our disappointment, if we look at this action space, the agent actually like does a lot of mistakes, such as it ignores the key information in the query, and it may not use the tools properly. So for example, this specification action here is trying to match the phrase from this query with the say the descriptions, the product descriptions. In fact, there's no single document that mentioned this phrase in the query exactly, so that will just lead to all zero scores. And this will eventually lead to poor task performance. And honestly, I don't blame the agents because this is a hard task and they are only given by the tools and they never, they don't even like use them before. However, it's still hard to think about like how to build a system that we can adapt those agents effectively and efficiently. So here's our framework, which is basically leveraging this contrastive reasoning ability for doing like better task adaptation. So thinking about a general setup where the user provide pairs of questions and answer, and also implemented some tools. So we can prompt the actor and agent to produce the actions, and those actions could just be the previous solution that you saw before. Differently, here we introduce a module called comparator. And what the comparator does is as follows. So the comparator will take the current action sequence, and it was mentioning that the current action sequence is applicable to like say multiple questions. So for example, think about like a batch of like similar questions. They are asking for different products, but like in similar form. Then we can apply the action sequence to each one of the question. So after that, two situations could happen. One is that the current action sequence can already get the answer correctly and produce like very good performance. And on the other hand, the action sequence may fail to give correct solution to some of the queries. So naturally, there's this separation of queries into two groups. One is positive, one is negative, based on their different performance. And then we prompt the comparator to reason over the pattern difference between these two groups of queries, and then trying to figure out how the pattern difference can lead to this difference in performances. And I will give a concrete example later. But to our interestingly, we found that this contrastive reasoning between the positive and the negative queries can generate a lot of insights on what's the right direction to improve in the actor's action sequence. And this updated insights or instructions can be used to prompt the actor again. So we have this like self-improving pipeline where actor produce action and the comparator doing contrastive reasoning and trying to teach the actor to produce better actions. So about how we does this, contrastive reasoning exactly, let's say we have an action sequence before, it does well on some queries, it doesn't do well on some queries, and the comparator take a look and realize that, oh, it seems that the actions perform well on queries with straightforward product features. So you can think about just simple queries like, oh, can you give me a red Nike shoes? Can you give me a waterproof jacket? Just simple queries. But it seems these actions fail to work on queries with more specific product descriptions and more implicit brand mention. So for example, there's no, the query format is more complex. It may even like mention, oh, can you recommend me a jacket that match the style of my shoes? Things like that. So apparently there's this pattern difference between the positive and the negative groups. And then by trying to, after getting this pattern difference, the comparison can work on more specific instructions about how to improve. For example, it should better parse the query attributes and so on. It should use like better tools for accurate brand matching, such as F1 tools, F1 score, and so on. So then this will used to prompt the actor and lead to like improved action sequence. And by a few iterations, the avatar can actually produce a very optimized like solution that correctly decompose the query, use correct tools, and lead to excellent task performance. And I won't go into too details about this example due to the time limits, but there's more details in our publication. But I do want to give another example in the image domain because I know people work on like image data and the video data and the multimodal a lot. So the task is kind of similar. It's a text to image retrieval. So given a natural language description, the agent should produce a sequence of actions that retrieve the image in a knowledge base. And here, each image is associated with some like like phrases, and each phrase is associated with some bounding blocks. And then we can provide the tools for the agent, such as get click embedding, get bag of phrases from the image, or even have this like small LLM function called like get attributes by like BQA and so on. So provided those actions, and it's interesting to see this contrastive reasoning works more broad than just improving the tools. And it could also improve the divide and conquer strategy. So after taking this batch of queries and trying to separate them into positive and negative, the comparator can then see, oh, it seems the action perform well on queries that are more often mentioned noun concepts such as woman, man, because visual concept is very complex. But for queries with broader set of other concepts like actions, like write, cook, or blue, or light, those are more implicit. And it seems like the current agent does not work well on them. So then this comparator will say, yeah, maybe you should consider separate extraction on the adjectives and the compound nouns and so on to consider this different aspects of concept to retrieve. And then this agent will just improve its actions by this better divide and conquer strategy. So for the tool part, similarly, for the image retrieval, there's the image is very heterogeneous. There are a lot of diversity inside, and maybe like some queries they actually mentioned they're actually requesting images from specific locations, and there are queries that like don't ask for locations, and sometimes like the retrieval pipeline may just ignore to consider location or not. So, but by this comparison and the contrastive reasoning, the comparator could give like more insightful instruction about maybe location is an important factor and valued a lot by the user. And now maybe you should use this tool, get visual attributes by LLM and trying to get location information from this image. And lastly, I think in the multimodal domain, sometimes people consider the, for example, scores from different type of data. I can do simple retrieval based on textual features, and I get the score solely based on textual similarity matching. And I can also do like image, like get image embeddings and get core embeddings and trying to match them. So there's different aspects of scores coming from this multimodal space. And at the end, we will want to synthesize them together. But the problem is like how much weight or how much value should we assign to different aspects. And we found that actually the comparator can also do this like numerical parameter learning or searching over this space. So for the performance, the avatar achieved better performance, especially compared to like some the other agent baselines and the clip model. So the clip model is also like implemented as a tool that the avatar agent can use. And also we also perform the avatar master on the Stark benchmark, which is also a benchmark developed by our Stanford team, which is trying to do retrieval in a complex textual and the relational knowledge base. And just to highlight, I think across the metric, since the agent master is very good at getting accurate results, then getting more comprehensive results. And you can just compare that by looking at the hit metrics and the recall metrics. And it's kind of interesting because I think now it's the advantage of the LLM agents that they can do use much more accurate reasoning and trying to get accurate answers. But of course, there's different aspects that you might need to consider in your system. And if the target is trying to get more comprehensive results, then maybe we want the agent better at getting all results together. And lastly, we also found if we look at this training curve along the improvement, and we can see the avatar can just quickly revise its solutions based on the insight provided by the comparator and in a very efficient way. And only I think for almost all methods, all data sets, only 50 iterations are needed to get a good performance. It kind of shows that the avatar agent can efficiently self-improve to conduct more accurate retrieval. So maybe a more high-level summarization of this work is that I think the language itself is very ambiguous, because if let's say we give an article to the LLM and we ask it to evaluate it, and the LLM could just say, oh, this article is very creative, it's very good. But sometimes we need certain reference in this setup to make the evaluation more insightful. And I can just give 2 articles, and the LLM will not just saying, oh, this is very creative. It will say, compared to the second article, the first one could be more creative, but also it make a couple of mistakes in terms of the grammar and so on. And this is interesting in our framework as well, where we are trying to have this contrastive reasoning to get more useful insights and more informative instruction to the agent. And another way to think about it is also an analogy to deep neural network training. And I think nowadays probably very few people trying to train a neural network and set a batch size as 1. And the fundamental reason for that is if we are using a very small batch size, and the gradient update will only target it at a very specific instance. And so does the agent optimization here. If we are trying to update the agent using a very, very specific instruction on 1 instance, then it could barely learn anything that's transferable to other instances. Instead, we are trying to have this batch-wise optimization to the actor, such that the improvement, the directions that pointed out by the comparator could be more useful in a general set of queries. Yeah, so I think and finally, I think now in our Stanford lab, we are also actively working on optimizing agents, and especially about these compound agent systems, where so going beyond single agents, the compound agent system, multiple agents, can do a lot of things nowadays, and it's getting interesting about how do we optimize them. And for this bigger pipeline, I think it's more powerful, but meanwhile, it requires a lot of manual efforts for people to look at the intermediate results and say, oh, this model is good, and so on. So I think optimization tasks on a more complex system will be very interesting. Yeah, that's pretty much what I want to say. Yeah, thanks, and feel free to ask any questions. I think I'm right on time.
So, yeah, thanks a lot, Shirley, for walking over the details. Very exciting work, and I think that notion of composite system, I think pretty attractive within the industry as well, right? Yeah, so the audience, if you have any question, feel free to just unmute and ask it directly to Shirley, or you can put it on the chat. Maybe just to get started, you mentioned some multimodal use cases, right? So image retrieval,
Yeah.
question answering, right? I think you mentioned a couple of evaluation tasks that be relevant for multimodal understanding.
Yeah.
I think numerical, for example, numerical calculation was one of the slides you mentioned.
Yeah.
Yeah. Just curious, what are the tasks that you think this framework can be very effective? I mean, what are the type of multimodal tasks, to be exact?
Yeah. So I think for the like textual, based tasks, like, reasoning, it's very easy to, put things in the LLM's context. But I think for the multimodal data, like image or videos, essentially like the agent would need to use like tools to target at them. And there's also a problem about like scalability, touching on that, because usually the say the knowledge base that the agent need to do the task would be in very large scales. And so there's this question about like how we can get to the correct solution with the, least cost or least latency. And I think that's especially important for like multimodal data, like, videos, for video understanding and so on. Yeah.
Yeah. And I think in the paper you make the separation between optimization phase and deployment phase, right? So this sounds like these are like two part of the pipeline, right?
Mm-hmm.
And so which part I'm curious which part is most compute intensive.
Yeah. I So in terms of the compute, for Avatar, because like very few iterations will be needed, and it also depends on like your input, like QA pairs, uh, and its diversity. So for example, if you only have a task base that have like 5 type of different questions, and I'm sure the agent can like quickly converge to that point. But if you have like just very, very diverse data, then it would be like take much longer for the agent to get to a point, get to a like that work for like every instances. Yeah, so there's also like some other relevant work, and they're trying to compare or have this like memory base where they store the question and they store some successful action like trajectories. But that tend to be very expensive because you can imagine the trajectory could be very, very long and then very like complex. So basically next time when the actor met like another question, maybe you need to like retrieve some relevant trajectory there and put in the context. But in context reasoning, meanwhile, is also sometimes not very stable. And I think we also try a very similar baseline, which is both computational intensive and not working so well. So yeah.
And just to double down on the comparator component of the framework. So I think in your talk, you're mentioning that like this is very important because it can refine the agent performance, right?
Yeah.
Via iterative generation of holistic and strategic prompts. Can you quickly go over again, like how did you like decide the prompt selection? Would that would that like via some sort of heuristic, or what was the rationale behind choosing the right prompts for the comparator to refine?
Yeah. So we didn't do honestly, we didn't do too much prompt optimization. I think the entire framework only used 2 different copies, actually 3. So prompt for the actor, prompt for the comparator, and the prompt for actor to improve based on the comparator's instruction, which is essentially the same template as the first one. We use very like minimum prompt, basically telling the comparator to, I think, contrast the pattern difference between the 2 queries, and then trying to like reason why the pattern difference lead to different performance, and lastly, come up with some instructions. So three subtasks that the comparator will need to do: compare, reasoning, and then give instruction. Yeah.
Great.
But I think the thing is, yeah, it's actually things are becoming more stable if you just do it like with multiple iteration, because you can see, so some like minor or small, you can call it like systematic error in the prompt could be eliminated, with like more iterations. Yeah.
And I think in the last paragraph on the conclusion of the paper, you mentioned that one future work can be designing better memory banks, right, for dynamically storing knowledge and experience from past training. What would we take? I guess what could it take to do that?
Oh, you mean like the memory base I just mentioned here? Yeah.
Yeah, the memory bank.
Yeah, I think yes, yeah, I do think memory bank is very important, but I mean people have very different opinion about that. One is, oh, memory bank is a way to reduce the context length for LLMs, but meanwhile some other people think, oh, the LLM's context will just go larger and larger, and we can just put everything. We don't need a memory bank. We just need to append the history. But I do feel like the memory bank is still useful because it will basically store, you can imagine like key value pairs, and every time you need something, you go to like do key matching and extract the corresponding value. So I do think it's a more like scalable way to do things. And I think also some other work explore how to even have an evolving memory bank. Yeah.
Okay. And then maybe last question is just about like the lab, the Stanford lab that you are affiliated with. Looks like a lot of the work your focuses on like generally like agents, but also about like aligning this agent with real world deployment, right? So that I think that's why the compile system piece is important, because that's how industry works. I saw that you have a couple other work recently, things like the benchmarking part called Stock. We do LLM retrieval, and then I think Graph Metro is another one that focus
Yeah.
on like mixture of expert. Can you maybe share some high level details about like maybe what are the interesting research direction that the lab is working on that might be interesting to the audience?
Yeah, so for ours, I just mentioned the future work, which is trying to optimize the component agent system. And it's very, very hard, I would say. It's very challenging sometimes, like, because sometimes the intermediates, it's kind of like similar to process supervision. Like we want to tell whether an intermediate output is good or bad, in terms of how likely it could lead to good or bad performance at the end of the pipeline. But sometimes the signal is very weak to learn. The correlation is very weak. So that's one thing we are working on. And also like we also work on another task about how to study the more human-centered AI agent system. So this is a recent work we just published this week called Collab LLM. And yeah, I do think that direction is very exciting. So basically, we look at like how we evaluate those LLM or LLM agents. We kind of view them in a very singular way. We test their performance on like math reasoning. We test their performance on like doing coding tasks. But when it comes to deployment, even with us like engineers or like with some other people who are using LLM to, for example, search for like ask about their symptoms as patient, usually there's this like multi-turn conversation with the LLMs. And nowadays we see the LLMs could just respond very passively. So for example, if I ask LLM, oh, I had a headache and I'm not feeling well, and the GPT will just give me like 6 different kinds of symptoms, I may or may not be applicable to me, or may or may not be understood by me. But if you think about like a patient walking into a hospital, and the doctor would just ask, oh, how long has the symptom been, and so on. So I think another exciting direction we are going into is how to build this like more collaborative agent that can, just work with everybody, especially like for some open-ended question. Yeah, that human are exploring. I think that would be extremely invaluable.
Awesome. That's great. Well, thanks again, Shirley. Thanks again for sharing your presentation today.
Thanks.
Okay, Zechen, it's your turn. Go ahead and share your screen.
Okay, cool. Let me try to share my screen. Okay, does that work now?
Yep, I can see it.
Okay, good. Then I will get started. So hello everyone. Thanks for joining this presentation and thanks for the intro. My name is Zechen, and today I would like to present one of my newest paper called VideoLISA, Language-Instructed Reasoning Segmentation in Videos. So actually in the domain of computer vision and the multimodal understanding, we can have such a kind of spectrum. Along the data dimension, we start with images and then goes to videos and even 3D data. And along the task dimension, so for each type of data, we have such tasks like very basic classification to detection and segmentation and so on. More recently, a more challenging task called reasoning segmentation. And we also noticed that there is actually a gap in the reasoning segmentation in videos, which is the kind of like the main focus of this project. We aim to bridge this gap in this whole spectrum. So before we start, we will first review a closely related work in image domains called LISA. So actually, LISA is a pioneering work on the image reasoning segmentation. So the task is defined as given an input image and a text query, and the model is tasked to output a segmentation mask of the target object. And the interesting part is actually the text query is much more complex than previous works. It requires the model to do some reasoning based on what knowledge and based on the input data, right? So in the work of LISA, it basically established an effective paradigm for the reasoning segmentation. That is, we can employ an LLM for understanding and reasoning, and they use a mask decoder for producing the segmentation mask. So that is the work of reasoning segmentation on image. And next, we will introduce the task of reasoning segmentation in videos and then see how our approach bridges this gap. So basically, in this task, we might want in the task of video object segmentation, we want the model to find the object in the video based on natural human instructions. So the very basic instruction is to tell the model about the object category. And more naturally, we may describe the object with some natural language, such as the cat near the camera. And if we take one step further, we have such an implicit expression that requires reasoning, especially reasoning along the temporal dimension. So for example, in this video, I plan to give one of my podcasts to my friends, and he actually prefers a lively and active pet. And which one should I give him? So it actually asks the model to find the lively and active pad in the video based on the action behavior of these two cats. So this is more natural for human daily needs, but also much more challenging for models to understand. And specifically, it actually requires the model to have such capabilities. First, it needs the model to understand spatial temporal information in the video content. Second, it needs to understand the human intent from language and reason the target object in the video. And finally, it should output a temporal consistent segmentation masks across the whole video, across the frames. So to build such a model, I think naturally we may want to inherit some experience from the image reading segmentation work like LISA, such as we can use the LLM as a brain for understanding and reasoning, and use a mask decoder to produce the mask. But when adapting this experience into video domain, we may encounter some problems like how to enable the LLM to understand video, especially in the context that video segmentation actually requires both temporal context and spatial detail. There will be often a dilemma. And on the output side, we may need to consider how to maintain the temporal consistency. That will be another problem. So to this end, we propose our framework. It's called VideoLISA. Here is a full illustration. So the model still take the video and the text query as input and use the large language model to reason, and then it output a special token. And then this special token is utilized by the mask decoder to decode the whole video into segmentation masks. And right, that is overview of the framework. And to mitigate the issue mentioned before, we introduced the following designs. So first, we want the model to understand video, and here is a strategy called sparse dense sampling to process video. So after the initial step of feature extraction from the video, we actually sample a list of sparse frames and compress each frame into one single token, while for the remaining frames, we regard them as dense frames and just keep their full feature resolution. So in that case, the sparse tokens are actually extremely compressed information, while the dense tokens are kept at high resolution. So the underlying assumption is that the information between the adjacent frames are somehow redundant. So the dense token can provide a visual detail for a kind of like a short time window, while the sparse token can capture the temporal changes with only small number of tokens. So in such design, the temporal context and the spatial details in the dense token can somehow complement each other. And it is also shown to be a favorable option for the dense prediction tasks such as segmentation. And we also show that in the experiment part. And next, we introduce another component, another design to mitigate the temporal consistency in the output segmentation masks. So to generalize the design of using a kind of like special token and a mask decoder to produce segmentation mask, it is natural to just extend the special token for each frame. Well, this is actually very inefficient from empirical study, especially for long videos with hundreds of frames. We may need to ask the model to output like hundreds of special tokens, which is very inefficient and also unstable for the current large language model. And it's also very challenging to maintain the temporal consistency for such a large number of tokens. So we consider like using just one special token to segment all the frames. This we call it one-token-seg-all. So in concept, we're actually trying to compress the object semantic information into this single token so that it can generalize to find the target object given any frame. So we start by testing some existing models and compare it with our VideoLISA. The main goal of this study is to see whether if we can get a special token from other models, can such special token be generalized across video frames to still find the target object, even the object have some movement or some other conditions. So first, in the vanilla segment anything model, we obtain a special token using a bounding box as a prompt and use this token to segment the object in the video. And we find that the first frame, it can correctly find the target object, the dog. And then with the movement of the target object, the localization can quickly fail. And next, we also experiment in the image-based work called LISA. And we initiate the special token using a language expression. We observe that this special token can somehow shows better robustness than the first model. But at least in the first 3 frames, it shows a good generalization. But in the subsequent frames, when some new object appears, the model still fails quickly. And lastly, in our VideoLISA model, the special token, as we see it, demonstrates strong robustness even with object movements, even with new object appears. It can always correctly find the target object. So we actually analyze the influence factor and design our model from the 2 perspectives. The first, on the model input side, we need to actually previous models only see 1 or only few frames, which significantly limits their kind of like the cross-frame generalization capability. While in our model, we have the sparse dense sampling strategy introduced before, and this actually serve as information foundation because the model can really see the video content, so it can reason across frames. And secondly, on designing the training objective, we actually explicitly enforce this single special token to handle multiple frames at the same time. So it actually encouraged the special token to learn a compact semantic information that is really generalizable across frames. And so actually in previous works, if without such a training objective, the special token is likely to learn a shortcut like the box prompt, learn a shortcut that's only focus on the spatial location of the current frame without considering the generalization aspect. Right, so here is a quick summary of the model part. We use M for reasoning, a mask decoder for outputting the segmentation mask, and additionally, we design a sparse dense sampling design to enable efficient and effective video learning, and also a one-token-seg-all approach to train the model using a one compact special token for the temporal consistent segmentation. And next, we'll briefly talk about how to evaluate such a novel task. Actually, we aim to evaluate the whole model comprehensively from these aspects, including both video object segmentation and image-based segmentation. And in the video part, we have general ReferVOS and more challenging motion-guided VOS, and ideally ReasonVOS. But we noticed that there is actually no benchmark for such a novel task in the community. So we also need to organize this benchmark by ourselves and to see how our model perform on this task. And specifically in the benchmark called the ReasonVOS we aim to emphasize the following aspects, including complex reasoning, word knowledge, and the temporal dynamics. And in the organization process, we consider that if you annotate the segmentation mask from scratch, that would be very expensive and time-consuming. So we choose to reuse the videos and segmentation masks in the 4 existing datasets, and we just re-annotate the language instruction by considering these 3 aspects. So you can imagine that the objects, the video, and the mask are still the same as the ones in previous dataset, but the language instruction will be quite challenging. It requires the reasoning word knowledge and also involve the temporal part. So that's basically the composition of this benchmark. And we'll show some experiment result. First, the model can achieve state-of-the-art performance on the general ReferVOS benchmark, including the RefDavis and the RefYouTube VOS. And similarly, in the motion-guided VOS benchmark, it still shows significantly better performance than previous work. And I would say this benchmark is much more challenging because it actually emphasizes the temporal aspect. I can provide an example from this benchmark. We notice that like the birds fly away, the cat playing with the teaser. So each tag query is actually emphasizing the temporal dynamics in the video. So it poses great challenge for the model to complete this task. And this kind of like verified the effectiveness of our model, especially the video learning strategy part. Right. Finally, in our self-organized ReasonVOS benchmark, our model still exhibit exceptional performance. And here, the interesting part, I think, is about the ablation study. We want to investigate the proposed model is particularly good for video learning. So we compare the sparseness sampling with a variety of approaches, like image-based LISA as a baseline and Q-former, and directly concatenating N-frame, there would be a strong baseline, and some other video learning strategies. And we observed that our design still achieves the best performance among these designs. This comparison actually gives some insights about how to design the video learning strategy, especially for the dense prediction task. So in short, we need to keep high feature resolution to complete this task because the dense prediction requires to access the visual detail as much as possible. And also the involving some temporal cues is also quite important, even if it extremely compressed into maybe single token, but it's also invaluable for this task. And next, this ablation, I think may only mainly want to answer this question. This is very intuitive. So for the task of reasoning segmentation videos, can we achieve that with just combining image-based reasoning segmentation model and a tracking model? And the answer is no. So we tried to experiment with image-based LISA combined with a state-of-art tracking model, and it still shows inferior performance compared to our model. And I think the main reason is that this model cannot really access the temporal changes in the video. So for a lot of data, it shows bad performance. And next, I will show some interesting qualitative example. So like this, personally, I really like this example because I just use one video to demonstrate various aspects of this model. So if I ask the model to simply ask model to segment the person on the left, the model can successfully find it. This is a very basic language referring. And then we ask model to find the object that moves fast in the scene. And then question requires model to reason upon what knowledge, and the model can successfully find the car in the background, even if it's located at background. And finally, we ask the model to find object that is moving faster in the video. And then the model can find the running dog that is actually moving faster than the car in the video. So this query actually requires temporal dynamic reasoning. So, right. Next, some more interesting examples, like how to ask the model to find the guy who need to go to hospital to get a checkout. And right, and even for this video example, this completely out of domain, out of the training data. I'm also surprised that the model can successfully find the target object simply based on the temporal changes the behavior in the video. And there are also some failure case the model cannot really solve. Like for the second example, ask a model to find which kid loses the game in the video. It always find the boy on the left. So it turns out that the model don't really have such or knowledge about this game. Then I explicitly tell the model, so in the game of the shown in the video, the loser will be hit by the face interfaced by a toy, then the model can successfully find the target object, the boy on the right. Right, that's a very interesting example, I think. All right, I think that would be the whole presentation of this work. I welcome any questions.
Great. Yeah, thanks, Zechen. Really exciting and I think definitely interesting qualitative examples towards the end after the show. Yeah, so I think we got like 5 minutes left. So if there's any question, please share it on the chat as you can put it on there. Or else you can unmute and just ask question directly. Maybe can you go back to the architecture diagram and awesome. Yeah, this is the V1 framework.
I have a quick question, if that's okay.
Yeah, please.
No, I was just curious to understand the improvement here is that one is able to ask questions about the temporal nature of different objects in the image. Like the dog is running faster than the car. Is that the innovation in this particular paper, please?
Right, I think it's kind of like one of the innovation. I think the main contribution is still the reasoning part. It's the reasoning based on various aspects. Like you mentioned that the dogs running faster is a temporal dynamic based reasoning. It also can work on the word knowledge based reasoning. So that would be another interesting part. And combining these these aspects from easy to difficult, combining these aspects into a single model, that would be the main contribution of this work.
I see. Thank you.
Okay, thank you for your question.
Yep. In the previous slide on the framework, can you go back again? You mentioned LoRa as part of LLM component. So LoRa, it's like a fine-tuned LLM, right?
Right.
And what was the purpose of fine-tuning in this case?
So actually, we also try not to fine-tune the model. I think that the main reason we fine-tune the large language model here is that first we need to adapt the original model into the domain of video object segmentation, but we don't really want to shift it too much, so we apply LoRa here. And another part is we need to train the model to output this special token, like the track token or maybe seg token in the original LISA work. So this special token will be used for the mask decoding. But if without this fine-tuning, the model cannot really generate such special token ideally.
Yeah, I see. And I think you mentioned the vision encoder and the mask decoder are both initialized from segment anything model, right?
Right. So the vision encoder and mask decoder are all initialized from the first version of segment anything. And I see there will be a lot of opportunity with the emergence of SAM2 because SAM2 is initially designed for videos. So it would be interesting if we kind of like replace the mask decoder with the SAM2 decoder or something like that. So I think that model can maybe handle the temporal consistency much better.
Yeah, that makes sense. I think that was my question as well. Yeah, so like for future direction, looks like, you know, upgrading these two encoder and decoder part with like better base model, right? Is one way.
Right. So actually replacing with stronger base model, that would be a viable future direction. And personally, I would be interested that from the task aspect, I think it would be interesting to kind of like involve the temporal grounding still into this single framework, so that like given an untrimmed video and a text query, the model can find the time window along the temporal dimension and the object across the spatial domain. That would be I think that would be a very useful application. And if we can do that in one single framework, that would be very interesting.
Mm-hmm. Yeah. And I think maybe last question I have is one thing you mentioned about the limitation on this work is around the computational efficiency, right? I think in the paper you mentioned that, you know,
Right.
you
So
go ahead.
yeah, at that time I mentioned the temporal efficiency, the computation efficiency is more like compare our model with the previous expert model on segmentation without using the LLM. So I think here even we tried with a much smaller large language model, we use 5.3, so it only like have 3.8 billion parameter, but it's still much larger than previous work. So I think that the efficiency might be a problem, especially if you want to deploy it in production, right?
Mhm.
That's the concern when we developed this model. But finally, later I found it turns out that there are some concurrent work that use much larger model. So the efficiency might not be a big problem. And there are also some mature technique to optimize this.
Yeah, I see. So it sounds like efficiency here doesn't necessarily happen to have to be implemented at the training phase, right? It can be implemented during the deployment inference phase.
Right. I think the training is somehow still efficient. So for training this whole VideoLISA, we at that time I don't really have access to A100 GPU. I only have like A10 GPU with only 24 gigabits. That would be also feasible.
Great. Awesome. Well, thanks a lot, Zechen. I think we had time. So really appreciate you presenting your work today. Yeah, and again, thanks, Shirley, for your earlier presentation. I really appreciate you both talking about this work. Thanks to the participants for joining, and I hope you learned something interesting. Recording of this webinar should be available online by early next week, so be sure to share that with the speakers. And once again, we run this webinar series on a weekly basis, so excited to see you in the future session. Maybe for this useful. Great, thanks everyone, and I hope you enjoy the rest of your weekend. Cheers.
Yeah, thanks.
You